Section 12.7, we're going to use our newfound knowledge of exponential equations and logarithmic equations to solve problems from the real world. And most of these problems involve things like interest, things like radioactive decay, where there's a constant exponential increase or a constant exponential decrease. And so I thought I would give you an example of one that has to do with money. So t, the variable t, is the time in years that your money is invested. K is the percent interest that's being compounded continuously, which is the best kind of compound interest you can get. The number in front of the e, the number being multiplied by the e, in most of this whole chapter is always the beginning amount of something. So this is the beginning amount of money you have invested. This function outputs p of t's, and those are the current balance at any given time. So let's make up a problem and see how we could solve it. Let's start out easy. Let's say that your initial investment is $1,000. And let's say that you were given that initial investment as a young child. It was from a grandparent's will who died, and your parents were clever enough to just put it in an account and let it sit. And let's say that the account was compounded continuously, and let's just say that your parents found a way to invest that over the years at 5% interest. And let's say that when you were 21 years old, so the time would be 21 years, you decided you wanted to go and find out how much money was in your account. Started out with $1,000, you got 5% interest for 21 years, and you're 21 years old and you're just kind of curious. So what do you do? Well, let's take this formula and let's plug in some numbers. We want to know the balance. This is the balance. The original amount was $1,000, so we put in 1,000 times E to the percent interest is 5%, but we write it as 0.05 because that's what 5% equals. It means 5 divided by 100. And 5 divided by 100 is 0.05. But that is going to be multiplied by 21. Because t is 21 and the percent interest is 0.05. So I'm going to take that and I'm going to put it in Desmos. So I've done the calculation here and it's almost $3,000. Now some people, when it's their money, like to play what-if games. What if your parents had taken a little more risk with the money, but they had gotten 10% interest, which is 0.10 or just 0.1? Then you would have had a little more than $8,000. So you kind of wish your parents had taken a gamble. And then let's say that they had taken a gamble and you decided that you were going to just leave it in there until you were 50. Because who knows, you might want to retire when you're 50. It's barely possible unless you love your job. That $1,000 in 50 years at 10% interest would be about $148,000. And you might think, wow, that's amazing. And it is amazing. People become millionaires by using this compound interest over and over and over again. That happens. But you've got to be willing to set aside a little bit of money. Like this money's set aside for 50 years. That's a long time to avoid that pile of money, but it was just $1,000 and it was given to you in a will, supposedly. And so this is the kind of thing you can do. Let's try a different version of the problem. So what happens if we say this? We're going to put in $1,000. And the interest is going to be 4%. It's a very conservative kind of investment. And we want to know how long, how many years it would take to double the investment, to make it twice as big. So what do? Well, we use this equation. We're going to put in $1,000. It's going to be at 4% interest, so we'll have a 0.04. We're asking how long. We don't know how long. It's going to be t years, and we want to know when it doubles. Now notice, it didn't even have to tell us 1,000. If we want to know when it doubles, we could put any number here that we want on the face of the earth, as long as this resulting balance is twice as much as it. We could have put in $1 here and $2 here, or $4 here and $8 here, or $1 million here and $2 million. The question is, what does t have to be for the 4% to go from whatever it was to twice as much? Let's scroll and let's maybe solve this. So let's divide both sides by 1,000. Now we've got an equation where the variable is in the exponent, so a good thing to do would be to take the natural log of both sides, or the log base 10 of both sides. Either one is on a calculator, so either one is acceptable. So now, well, I want to move this over a little bit because I want to bring this exponent down in front and multiply it by it. And then I'm trying to get the t by itself, so I divide both sides by this. And then I'm still trying to get the t by itself, so I divide both sides by this. And I have t equals the natural log of 2 divided by 0.04 times the natural log of e. But the natural log of e is the power you raise e to get e. What power do you raise this thing to get itself? Well, the answer is the first power. So when you see the natural log of e, that's just 1. And so t is going to be the natural log of 2 over or divided by 0.04. Natural log of 2 divided by 0.04, so 17.32 years. A little bit, I'll just call it 17.3 years. It takes 17.3 years to double. Why so long? Because 4% interest, while being good, isn't spectacular.